Hello, guys, this is Keys to the Truth, and in this episode, we will be taking a chapter from a book called Out of the Crystal Maze. I will be reading and adding some of the commentary. A lot of the people are still wondering if crystal magic is real or not. What makes up matter? What makes up the universe or the cosmos or this earth or this realm or this construct, whatever you want to call it, what makes up nature. I've already showed you that. If you, in case you haven't watched it, please check out my video on how atoms and molecules do not exist. They are a fantasy. They are bogus. They're hoax. They're just CGI construct. So what really makes up matter? Matter is composed of crystals. You heard me correctly. So if you haven't watched my video on what makes up matter, finally exposed, you can do that now and then come back to this later. You can also watch my video on why they build skyscrapers. And I have several more videos discussing this fact. Now, upon doing some research, I found a particular academic book on physics. So this is the hardcore academic stuff where they're showing you their craft from the inside. And this is very important because you get a certain validation. And it's not that, hey, we need to get validated. It's not that sort of thing. But it is a point of reference in our search for truth. Remember, we do not necessarily know what the truth is. Only God can reveal us the truth. So He's giving us different tools, which I call the keys to the truth. And when you're trying to determine if something is fact or fiction, it is very helpful to have these points of references that, again, I call the keys to the truth. So one of them is going to be what academics know, what academia knows from the inside. And their doublespeak, their duplicate system becomes obvious. You become aware of it. So anyway, let's get started, and you will see, it will be revealed to you and I that at the highest level, at the very top level of academia, they absolutely are aware of this. And I don't mean like regular professor. I mean like the highest echelon. They are aware of this. They know this, and they're studying it. They've been studying it for over 100 years. But let's dive in. So, Out of the Crystal Maze. Reading and commentary. Chapters from the History of Solid-State Physics by Lillian Hudson, Ernest Brown, Jürgen Teichmann, Spencer Weert. All right. So I'm not going to read everything. I'm just going to read a few lines that stand out. Table of Contents, Chapter 1, The Roots of Solid-State Physics Before Quantum Mechanics. This one is written by Michael Eckert, Helmut Schubert, Gisela Torka, with Christine Blondel and Pierre Kedek. Right? So here we go. The title of the book itself is what caught my attention, and it's what ultimately led me to buy the book, because there wasn't a lot of information about it. It just says Out of the Crystal Maze. And, it is delivering. It is delivering. You'll see here in a minute. It's not just a fancy title, but they're actually giving you a wink nod that they're telling you that they know what's really going on. So here we go. The plain goal of science is to understand use the objects around us. And of these objects, the most obvious are solids. They are among the first to be mastered and among the last things to be understood. The growing ability to manipulate stone, then ceramics, then glass, metals, jewels, and so forth was central to the history of the human race. If there was no corresponding progress in finding concepts that could unify the understanding of solids, it was not for lack of trying. The works of Greek philosophers, medieval alchemists, and 17th century Cartesian natural philosophers abounded in fanciful models of the solid state. Then, as Cyril Stanley Smith has pointed out, the breakthrough of the new quantitative science interrupted the age old tradition of qualitative thought about the properties of solids. Properties such as color and hardness, even after people learned to measure them, could not be calculated with the concepts at hand. Those who strove to do physics on the model of Galileo and Newton had to set these questions aside and abandon everything that depended on the detailed interaction of many parts. With reference to metallurgy, Smith noted that the era of Descartes was the last time for 3 centuries that respectable thinkers concerned themselves with the properties of real solids. There's a lot of hidden information here, guys, that you need to read between the lines. Why are they talking about jewels and glass immediately? And then they're talking about the Greeks, and then they're talking about alchemists, and then 17th century. And he's mentioning Descartes twice in the same paragraph. So just keep that in mind as we move along. I don't want to make this longer than necessary. So just keep those things in mind, and then I'll sum it up. Unifying concepts that offered a genuine ability to calculate the properties of solids had to await the coming of quantum mechanics. But even after the first application of quantum mechanics to solid state problems in the 1920s, over a decade would pass before anything emerged that physicists would recognize as an independent discipline devoted to the solid state. The history of early solid state physics is thus a subject that does not exist. What we have instead are histories of a bewildering variety of separate topics. It is impossible to answer every question about every discovery that fed into what eventually became solid state physics. Hence, we will indicate the general scientific, institutional, and technical background from which such studies of solids emerged before they were combined to form an independent area of physics. In particular, we indicate the points of departure for the developments treated in this book. Therefore, most of this chapter covers the first decades of the 20th century, along with some brief remarks on the 19th century institutional framework. We shall see how deep and varied are the roots of solid-state physics, but we shall also see how the different studies of solids themselves contributed to the unified understanding on which the new field would eventually be built. The differentiation of scientific knowledge into the spectrum of separate disciplines recognized today began in the 19th century. Solid-state themes were isolated from one another in this process, and research was recorded in the context of disciplines that had diverse problems and goals. Themes such as crystal chemistry and the properties of metals became topical in newly institutionalized and for the most part isolated areas of chemistry, mineralogy, and engineering, which flourished in mining schools, the revived universities, and the recently established polytechnic schools. So notice that he mentions crystals right there. First time he mentions them outside of the title of the book itself. So let's continue. The institutional base, that is, the source of the money that made research possible, had much to do with practical affairs. This was quite important for research on solids, as we shall see throughout this chapter. The industries that blossomed in the latter 19th century, particularly the electrical industry, placed new demands on science. State and industrial research institutes occupied chemists, engineers, and physicists with problems of cables, the fabrication of filaments for incandescent lamps, and the investigation of alloys for standards of electrical resistance, among others. In the face of intense international competition, it became more and more important for certain branches of industry to take academic research into account. Conversely, academic physics was influenced by new questions that arose in industrial contexts. For example, the engineering question of the temperature dependence of the electrical and thermal conductivities of a metal or an alloy played an important role in theories about electrons and thus made it into academic discussion. Remember, electrons are fake, they do not exist. It's just part of the hoax. But let's continue. Meanwhile, the world view of academic physics changed radically. Since the early 19th century, crystals, for example, had been studied primarily in the abstract as the idealized systems in which the interplay and symmetry of the forces of nature could be examined. The existence of microscopic elements such as atoms could be inferred because they don't exist, right? But almost nothing could be learned about them. You can't learn anything about something that doesn't exist. So again, beware here of the doublespeak. The writer may actually be aware of it or not, okay? Because the mind control and the conditioning is just so entrenched. So, and you can see it in all the hoaxes that they pull, like the current hoax, the past hoax, the next hoax, all the hoaxes. You see people, they have this veil over their eyes and their mind, they can't even see things that are just plain for you to see. So hopefully you are one of the people that have seen, given the divine vision by God. But see, let's continue here. So just again, remember they have a duplicate system, a double speak. Atoms and molecules, they use that to hide the stuff about the crystals, which is the real stuff. So let's continue here. The existence of microscopic elements such as atoms could be inferred, but almost nothing could be learned about them. The great 19th century advances were in macroscopic concepts, such as the laws of thermodynamics and electromagnetism. But at the end of the century, new concepts of statistical mechanics, electrons, and ions. An ion, remember, is an energized crystal. Combined with the discovery of X-rays, of radioactivity, and of Planck's quantum revolutionized physics, these concepts were a breakthrough in microscopic models, which would eventually explain a multitude of properties that had previously been handled only phenomenologically. I'll tell you about quantum physics here in a minute. So let's continue. As a rule, the revolutionary new thought was not aimed primarily at solids in their diverse manifestations and properties. Rather, many effects in solids, most of them known for a long time, served as objects upon which to test and develop the new theories. The treatments of the specific heat of solids by Albert Einstein, Peter Debye, Max Born, and others provides an example of a solid-state theme that was also a forerunner of quantum physics. The breakthrough in microscopic concepts, which together with quantum mechanics achieved a unified formulation in the mid-1920s, was not purely a matter of theoretical physics, for new experimental techniques were equally important. Thus, the efforts of theorists to grasp the prominent effects of the quantum at low temperatures advanced in parallel with the drive toward ever lower temperatures, which led to the discovery of unexpected phenomena such as superconductivity. Other important examples may be found in spectroscopy, where discussions of the thermal vibration of the atoms and solids were intimately connected with infrared techniques, which could be practically applied. Substitute the word there, atoms, for crystals. So it's the vibration of crystals in solids, etc. That science was more than just an intellectual endeavor became evident to all during the First World War. Those states that had underestimated science as a tool of power now began to take institutional measures along the lines already taken, for example, in Germany, with the establishment of the Kaiser Wilhelm Foundation in 1911, national research councils, cooperation between academic research and industry, and the state and private research support began to be organized. Typical groups were the Department of Scientific and Industrial Research in England and the Research Institute of Iron and Steel, as well as the Institute for Physical and Chemical Research in Japan. And many of these institutions were concerned with specialized solid-state research. For example, Kaiser Wilhelm Institutes in Berlin, Dahlem studied metals, the chemistry of fibrous materials, and silicates. The Japanese RIIS supported Kotaro Honda in his magnetic and metallurgical research. After the First World War, these organizational efforts were systematically continued, so that solid-state research was institutionalized and financially supported in many places in the 1920s. Review articles, textbooks, handbooks, and conferences of the period provide evidence that themes like the electrical conductivity of metals and the dynamics of crystal lattices were considered as identifiable areas of current research and were already integrated into the main body of physics instruction. However, there was still little evidence, institutional or intellectual, for the existence of a fully formed and independent discipline of solid-state physics. This chapter spans the period from the beginning of the 19th century to approximately 1925. Using representative cases, we sketch the background on which solid-state physics would eventually appear. We will not discuss some specific developments that are covered in their full context in later chapters. For example, point defects. In addition, many other important developments are omitted. The events that we discuss usually appear as unconnected incidents because they were not connected except by the broadest economic and intellectual themes, and it is only hindsight that singles out these examples as parts of an eventual solid-state physics. A mosaic representation is almost inevitable in any case when several authors with varying backgrounds and interests write a single chapter, but we hope the very heterogeneity of the mosaic will show how solid-state ideas emerge from a multitude of contexts and were combined into subtle patterns that can be comprehended only from a distance. So they're being all punny there. They're giving you so many puns referring to the crystals. Mosaic, right there. Heterogeneity, again, mosaic, they write it twice. Multitude, subtle patterns, comprehended from a distance. So again, guys, you have to look for what's hidden between the lines. So let's carry on. Get your coffee first. Or, if you like tea or if you don't drink tea, get your water. And make sure you check out my new website, which is keystothetruth.com. So we can stay connected there. You never know what's going to happen with these platforms. Their rules change, their censorship changes. Right now, I'm kind of flying above the radar, above the pay grade of the censors, but let's hope it stays that way. This stuff is just far above their heads, but you never know. So please bookmark the website, keystothetruth.com, and sign up so that we have each other's email. My email is keystothetruth@gmail.com and also info@keystothetruth.com. So when you subscribe to the website, I'll have your email, and then you can always email me. If you want to opt out, you can opt out. You can put me in your spam folder, whatever the case. But the thing is that we stay connected if you want to do so. And we continue this conversation and this exchange of ideas and exploration into the world, which is by definition an exploration into God. Okay, so let's continue. Chapter 1.1: Institutional Settings for the Scientific Investigation of Solids in the 19th Century. And just be a little patient. You may want to skip along this if you want to find where they start talking more about the nitty-gritty of the crystals, or you may want to join for the whole thing, whatever the case may be. So I'll carry on. The Industrial Revolution and the rise of the bourgeoisie at the dominant class as the dominant class during the 19th century imposed new conditions on the organization of society, giving rise to many new institutions. Some of them were devoted to scientific investigation of the properties of solids. There were forerunners of such institutions even before the 19th century. In some states, the extraction and processing of raw materials were supported by absolutist rulers in order to enhance their financial power and military strength. In particular, the extraction of precious metals had been a source of feudal wealth for centuries, and this wealth was increased by the raw materials of industry, whether imported from colonies or mined at home. But many sites could be mined only at the price of increasing effort. Governments therefore founded specialized academies, such as the Austro-Hungarian Berkada Academy Chemnitz in 1770 and the École des Mines 1783 in France. Oh, go wonder, why the 1700s? Geez, guess what happened? They were plundering India. They were getting all the ancient texts they could, because by that time India was in decay. They didn't know what was what. They had forgotten their roots. They didn't know what they had and the value of the ancient texts they had. So the British went in and they plundered everything, and they found these ancient texts, ancient artifacts. They took them all back and they started studying it and developing the Europe and all of industry in the 1700s. So my point is not like, oh, John versus Paul or this versus that. No, my point is that our human civilization was much more advanced in the past, like super advanced. I mean, hundreds, if not thousands of years ago. Then, for whatever reason, there were huge destructions, and we can see that all over, evidence of that all over. But a lot of the knowledge remain, a lot of the artifacts remain, and they've been hidden from us. They've been stolen. They've been, and they're keeping the knowledge to themselves, and then they sell it off to the academia, and then they develop that for industry. So that feeds into the monstrous complex that we see today. But do not fret over the workings of evil, but rather expose them, as the Bible teaches us, and always trust in God and know that He is in control. So let's continue. Technological questions attracted scientific interest especially in the new French schools, where methods were developed to investigate such matters as the strength of materials. In the Berg Academy Chemnitz, mineralogy was taught with the aid of magnificent specimens of gold and iron ore. Calcspar, geognostic pieces, especially of granite, sienite, and crystal models made out of gypsum, while a laboratory equipped with regal splendor fostered clear empirical instruction. In 1794, in the midst of revolution, the French state founded a new kind of institution, the École Polytechnique, which would become far more than an engineering school. It was meant to serve as a preparatory school for the reformed or newly established engineering schools for mining, artillery, civil engineering, surveying, and shipbuilding, providing students in these specialties with a broad scientific foundation. Under Napoleon, the school was assigned to the War Ministry, and students could look forward to careers as officers in the Imperial Army. Professors, as well as students, enjoyed great social prestige. The publication of a journal, as well as the obligatory publication of the professor's lectures, provided stimulation, a specialized body of knowledge, and a high standard. Teaching came to be seen as linked to research, which included both theoretical and experimental investigations. The overriding goals were to reduce empirical observations to mathematics and to attain the greatest possible precision in experiments carried out in the special laboratories that had been set up for teaching. There are many examples of the role played by the École Polytechnique and other engineering schools in the development of physical science. In the area of solids, professors conducted important studies in the theory of elasticity, strength of materials, thermal conductivity, and optics. Many such investigations were closely tied to applied problems. Thus, Louis-Marie Henri Navier, a Polytechnique student employed in the 1820s as a professor at the École des Ponts et Chaussées, the civil engineering school, was interested in the construction of iron bridges which were just becoming into use. In his Louis de l'équilibre et du mouvement des corps solides, he used molecular conceptions to develop the differential equations for the elasticity of three-dimensional isotropic bodies. This approach to solids, combining a concrete model with abstract mathematics, was so fundamental that physicists eventually came to take it almost for granted. The example of the École Polytechnique influenced other countries. The United States Military Academy at West Point was organized in 1802 along similar lines, and through the 19th century, this was one of the most progressive American institutions for scientific instruction and research. In Europe, especially in the German states, the model was imitated in polytechnic schools from which many technical universities later sprang. So this is all talking about social engineering, if you notice. Let's continue. The next great impulse toward educational reform came in the early 19th century in Prussia and spread throughout Germany. Associated with the reformers was an idealistic neo-humanist ethos. Scholarship should be free from ulterior motive and carried out for its own sake. Really? Oh God. The irony. Let's continue. The circle of existing German universities was imprinted with a new ideal, summarized in the motto, freedom to teach and freedom to study. Yeah, what they want you to know and what they don't want you to know. So let's continue. Thus, teaching and research presented a unified front. The reform movement proclaimed education for its own sake to be a duty of the state. If it's so free, then why does the state have to take control of it? Oh my gosh. And the educational system became the responsibility of a state cultural ministry. When these ministries came to choose men for university positions, they began to use recognized achievements in research as an essential prerequisite. This research imperative for professional careers made research at the universities a regular professional activity. So they took control, basically. The new supremacy of research opened the way for new characteristics of science to evolve. A reform that strove toward humanistic education paradoxically ended up encouraging the dissociation of science from philosophy and a progressive specialization into independent, professionalized disciplines. The era of the amateur was ending. Right, and why are you separating philosophy from the practice, from science? Because they don't want you to think, they just want you to do. At the same time, a polytechnicism, or whatever one wants to call the materialistic aims that some researchers adopted, increasingly conflicted with their former ideals. Toward the end of the 19th century, the conflict would erupt in intense struggle as the engineering schools demanded a status approaching that of the universities. Nevertheless, the coexistence of training and education, or of soul, Geist, and industry, as slogans describe the division, broadened the range of possibilities for both scientific and applied activity. This book was published in 1992, by the way. I hadn't said that, but I'll put it here in the slides. 1992. So let's continue. The strength of the German universities was much admired in England and helped lobbyists for science to argue for increased national support of both research and teaching. Here, where the Industrial Revolution was born and where a prosperous middle class surpassed the old feudal and clerical leaders of society, earlier than on the continent, new institutions and societies were organized on a private basis. Not Oxford and Cambridge, but dissenting academies and mechanics institutes, most often founded in the aspiring new industrial cities, were breeding grounds for research oriented toward the needs of industrial society. For the first time, a significant number of people earn their living explicitly by doing research as well as teaching. Another indicator of the establishment of a new class of professional scientists and engineers was the founding of associations for the support of science. In the mid 19th century, scientists in many countries banded together in such associations, which brought new pressure on governments to increase scientific instruction. The new associations also reflected the differentiation of science, as seen particularly in the case of the Gesellschaft Deutscher Naturforscher und Ärzte, founded with subdivisions in 1822. The organization by 1894 had 41 specialized sections, including geognosy, mineralogy, chemistry, physics, technology, and mechanics, to name only those relating to the investigation of solids. In the second half of the 19th century, some scientific disciplines achieved complete independence. Metallurgy, mineralogy, chemistry, and physics became well-organized areas with their own specific interests and methods, gathering and disseminating information in their own separate research institutions, societies, and organs of publication. Now more than ever, when solids were studied, they were studied with the boundaries of one or another of these new professional disciplines. Engineering, chemistry, and physics as specialties. It may be quite true that many of the practical and technical details of civil engineering may be best learned in the offices of engineers engaged in the execution of important works. But the knowledge of mathematics and mechanical, and I've told you what math is, be sure to check out my video, What is Math? It's not what you think. But the knowledge of mathematics and mechanical principles as involved in the estimate of the strength and distribution of materials, the effects of elasticity, and generally of the operations of forces and pressures is so necessary in all the more important and difficult applications of this science that no amount of practical skill and experience can ever replace the want of this theoretical knowledge. In such terms, a need was formulated in mid-19th century England that there and in other countries caused the study of solids to be institutionalized as part of engineering. In particular, knowledge of elasticity and the strength of materials was crucial for such mechanical engineering tasks as constructing railways and erecting large buildings of iron and reinforced concrete. That's what I tell you. They can try to hide the duplicate system as much as they can, but ultimately, if you want to do stuff, you have to have some inkling of what's really at work here. Okay, so let's continue. In technical universities like the Eidgenössische Technische Hochschule, founded in 1855 in Zurich, and the Munich Polytechnium, regular engineering instruction came to include subjects such as construction materials, metallurgy, mineralogy, and crystallography. Let me repeat that again. Crystallography. In the 1870s, many of these engineering schools set up laboratories for materials testing, where properties of iron and steel became the principal object of intensive research. The practical goals were explicitly promoted by new social organizations in which engineers were coming together. For example, in 1877, a Technische Kommission des Vereines Deutscher Eisenbahnverwaltungen, a railroad group working toward a national standard for iron and steel classification, insisted on the need for better knowledge of the properties of materials. For the investigation of these laws, we propose the establishment of a research institute. Said the Technical Commission, and it formally moved that the Association of German Railroad Administration bring its considerable influence to bear in order that this conviction also takes hold within the government and in order to bring such institutes to life as soon as possible. Other striving industrial nations, particularly the United States, also had a blossoming of technical teaching institutes. As a German observer reported in 1894, the number of American technical teaching institutes is enormous. There are now already over 200 on record, with new ones still to come. The curricula of new technical universities, such as the Massachusetts Institute of Technology, MIT, founded in 1861, showed that here too the essential components of engineering began to include materials testing, the theory of elasticity, and similar problems of the mechanical behavior of solids. Chemistry provides a second example of the incorporation of solid-state themes into an emergent specialty. Subjects like mineralogy and crystallography again, had long been of practical importance for mining, but they became increasingly useful for chemistry as well. The usefulness hinged on the recognition that similar chemical compounds correspond extensively in their crystal form. Read that again, extensively in their crystal forms. Thus, the tremendous upsurge of industrial chemistry, one of the central transformations of the 19th century, aided mineralogy and crystallography. For example, it was a combination of chemical and crystallographic research inspired by interests connected with the French wine industry that led young Louis Pasteur to discover that tartaric acid can have two forms that are chemically identical but physically different. Well, and we know that guy was just one of the hoaxers, big hoaxers of all time, and part of the system, the evil system. So take that with a grain of salt. Let's continue. A crystal of one type rotates polarized light to the left, and the other turns it to the right. So again, crystals, 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 and now we're getting to the nitty gritty of the text here. You see, you're going to start seeing crystals right and left, and let's continue. But light does not move. Check out my videos on light, what light really is, how light travels, and again, light is a property of matter. It's a property of crystals. It doesn't travel. It's not a thing that goes from A to B. But check out the videos and then tell me your comments. Let's continue. Later, in 1874, Jacobus van 't Hoff and Achille Lebel learned that this sort of optical activity is caused by the asymmetrical positioning of carbon atoms in organic molecules. Forget about the atoms, man. That's just the double speak to try to fool us. Studying such interactions between molecules and light became a main concern of late 19th century physics. Again, a bunch of hooey. Such work would eventually be at the center of solid-state physics, but at the outset it was a chemistry technique. Organic chemistry, busily giving rise to new industries such as the production of artificial dyes, urgently needed crystallography to identify and classify the rapidly growing number of chemical compounds. So, what do they use to classify chemical compounds? Did they use atomic electron scopes? Did they use molecular stuff? No, because atoms and molecules do not exist. They used crystallography, and it's the same thing that we use to this very day, because that is what makes up matter. And I'm showing here what academia thinks inside, okay? Not from the outside, not in pop science, not in the media, but academia, okay, at the highest level. Let's continue. Long before the discovery of X-ray diffraction in crystals, chemical crystallography, carried out in new institutes founded expressly for the purpose, brought an abundance of crystallographic investigations, chiefly of organic compounds. Physicists were meanwhile forming their own professional organizations and establishing their own characteristic problems, which naturally included problems of solids. A series of phenomena such as thermoelectricity and the Hall effect were discovered and studied as part of the general program of physics. But such phenomena were not grouped together under the general heading as questions of the solid state. Rather, they were placed as seemed best among the classical subdivisions of mechanics, heat, electricity, magnetism, and optics. Where special areas like crystal physics was touched on, as is discussed in what follows. The physicists were chiefly interested in overriding fundamental ideas, things that could be taught to students as examples of generalized mathematical and instructive principles. The archetypal physicist's attention was directed toward ideal crystals, in hopes of progressing inward toward the molecules and atoms themselves. I remember, they have to lie to you somewhere to keep you from the truth, okay? But you know better. This direction was opposite to that followed by chemists, metallurgists, and engineers who concerned themselves with real solids such as steel. This does not mean, however, that physical research and instruction were everywhere removed from practical needs. In the 1870s, practical physics became a catchphrase for a movement under which new laboratories were founded at universities and engineering schools, along with corresponding laboratory courses and textbooks. The basic subject of physics proved well suited to help out industry, particularly as physics-based industries spread. These industries required an international effort in measurement, calibration of instruments and standards, all based on proven scientific principles. Thus, practical investigation of materials moved into the realm of physics. For example, physics principles and experiments were required by those who calibrated thermometers by using the temperature dependence of the electrical resistance of certain materials. Other problems were found according to the foreword of Friedrich Kohlrausch's textbook of practical physics, published at the end of the century. In the subtler parts of optics, in photometry and thermal radiation, but especially in the theory of electricity, where the determination of magnetic and dielectric constants have been given a wider place than they had before. The academic physicists still did not see studies of solids as gathered together in fundamental research program. What was studied depended on the accidents of interest in particular applications, yet this new interest in problems of solids helped physics to get increased attention from industry and the state. The influence of industry, cryogenic steel, and electrical engineering. As scientific laws, or at least scientific methods, were increasingly applied to the production process, industry became a main source of employment for graduates trained in science. The professors were naturally interested in the problems of the industries where their students were headed, and this interest sometimes led to the new results of a strictly scientific nature. The study of matter at very low temperatures, which would eventually have particular significance for understanding properties of solids, is an example of a field that began among highly practical interests. For one thing, increasing trade and the growth of cities raised the need to cool food on long transport routes and in warehouses. For another, chemists were interested in using low temperatures to liquefy gases, an interest connected with the search for an easy extraction of nitrogen and oxygen gases that played an essential role in the chemical industry and steel production. Many engineers took up construction of different sorts of refrigerators. Carl von Linde was the first to apply himself to the question of the efficiency of refrigerators. At the ETH in Zurich, he studied mechanical engineering and attended the physics lectures of Rudolf E. Clausius. Employed in 1868 at the age of 26 at the Technical University in Munich, Linde advocated this practice of giving instruction in theoretical mechanics along with practical machine construction. Along with theory, he was given responsibility for applications since he had worked in several industrial concerns. Making a systematic comparison of refrigerators processes, he found that existing ice machines reached at most 10% of the theoretical maximum output. With the financial support of a Munich brewery, he succeeded in his first attempt to construct a machine which doubled output. Encouraged by this success, Linde founded his own firm, which took up so much of his time that in 1879 he resigned his professorship. Linde's combination of basic research and practical results emerged again in 1892 when he took up his university career once more investigating methods for liquefying air. Within a few years, he constructed the first economical air liquefaction equipment. The new method was put to work by James Dewar in the Royal Institution, who carried systematic investigations of the properties of solids down to a temperature only 20 Kelvin above absolute zero. As in cryogenics development, so in the steel industry, the application of scientific methods to traditional processes led to marked improvements. The tremendous increase in demand for iron in the 1850s, mainly for railroad tracks, showed up the limitations in the hearth refining and puddling processes for making iron. In London, Henry Bessemer found through laboratory experiments a more efficient way to make steel, but he lacked exact knowledge of the chemical reactions involved and encountered many difficulties in putting his ideas into practice. A little later, the chemist Robert Wilhelm Bunsen and the physicist Gustav Kirchhoff developed spectral analysis. A pupil of Bunsen used it on the light from the flames in an English ironworks and found the conditions for the optimum air supply in the Bessemer converter. Spectral analysis. So the color tells you what something is made of. And that is how we know what the sun is made of. And that is how we know what the moon is made of. But I will go into those topics in other videos. The new discoveries help bring a sharp rise in steel production. Production in the Krupp firm, for example, increased from 5,000 tons in 1861 to 50,000 tons in 1865. The importance of science to steel production was now evident, and all the larger producers changed over to the new methods and hired chemists. The increase in steel production also boosted the importance of metallurgy as an engineering science. In Germany, France, England, and the United States and Russia, important works on the structure of solids appeared between 1860 and 1890 in engineering journals. These studies used iron and steel, not simple solids, as examples. For example, Dmitry K. Chernov, a Russian metallurgist, reported on the fracture grain size in steel in relation to heat treatment and carbon content at various temperatures. He also investigated dendritic crystal growth. His point of departure was observations made during the forging of guns. Chernov was one of the first to notice that the properties of materials are directly connected with their crystalline fine structure. Again, I'll read that again. That he was the first to notice that the properties of materials are directly connected with their crystalline fine structures, and that casting, cold working, or heat treatment determines the quality of the production by influencing this structure. This here is a bomb, and this has so much depth and so much knowledge that we will need to revisit it. So they're telling you what goes into making a crystal, the different energies, the heat, the pressure, all that is going to determine the properties and the structure of the crystal. Keep that in mind as we go into further videos and we unravel the mysteries of this world, or more correctly put, God reveals them to us. By His grace, blessed be He. Anyway, let's continue. In 1878, the Zeitschrift des Vereines Deutscher Ingenieure published an article on the microstructure of metals written by a bridge construction engineer of the Prussian Railroad. The article showed that metals could be analyzed by etching thin sheets with acid and observing them through a microscope. This method, which beautifully reveals the grain structure, was developed into an independent branch of science by Henry C. Sorby in Sheffield, a center for the English metal industry. In contrast to such traditional industries, the nascent electrical industries were closely linked to scientific research from the start. No practical use could be made of electricity until disinterested research had revealed some of its basic phenomena. One early application was electric telegraphy. The electric telegraph's utility for trade, railways, and military maneuvers soon caused it to grow into a profitable industry. By the middle of the century, the European nations were linked with one another by copper wire. The connection between continental Europe and America, and between Europe and its colonies, became an international enterprise inspired by the needs of trade. The completion in 1866 of a permanent telegraphic connection between the stock exchange centers on Wall Street and London was celebrated as one of the greatest technical accomplishments of the 19th century, and also about control. Because money is all about control. Money is a spell. That's what it is. Let's continue. The problems that arose during this undertaking, such as design of insulation and cable strength, were overcome by the collaboration of scientists from various disciplines. For example, in 1864, the chemist August Mathiesen developed a method to control the purity of copper. still one of the standard methods today. He discovered that the specific resistance of metals is composed of the sum of two components. One depends on the temperature and the other measures the purity of the metal. Mathiesen learned how to separate these components through measurements at varying temperatures, and thus could compare the purity of every type of copper found in trade. The explosive growth of the electrical industry from 1880 to 1900, for example, the number of people employed in the industry in Germany rose from 1292 in 1875 to over 18,000 in 1895, gave still greater impetus to the investigating property of solids. The development of electric illumination now took the lead. The carbon arc lamp, which was turning night into day on the streets, in public buildings, and in factories, was the point of departure for the discovery of the anomalous temperature dependence of electrical resistance and the anomalous specific heat of carbon. When incandescent lamps eclipsed gas illumination in private households toward the end of the century, thus giving rise to a huge branch of production, these lamps also became a lucrative object of research. For example, in 1888, H. F. Weber, professor of theoretical and applied physics at the Zurich ETH, published a relationship between the change in the wavelength of light emitted by a glowing body and its temperature, from which all properties of the electric incandescent light, except for the lifetime of the lamp, could be deduced. Such work paved the way for Max Planck's radiation formula and the quantum theory, but at the time it had a distinctly practical flavor. Practical electrical research that would lead to the fundamental understanding was embodied in towering brick laboratories. In addition to universities, corporations such as General Electric and Philips created these laboratories with the original intent of studying lamps, but scientific results of broader interest flowed out. The telephone was another electrical device that furthered the tendency to establish basic research in industrial contexts. In the United States, at the turn of the century, the Bell Telephone Company was among the first corporations to set up a research laboratory, which eventually became one of the greatest centers of solid-state physics. Many such institutions were founded to bring academic and industrial science together. We will look in more detail at two that illustrate the range of possibilities. The Physikalisch-Technische Reichenstalt and the Göttinger Vereinigung. The more closely new technologies, such as the telegraph, brought nations together, the stronger was industry's call for standardization. Precisely defined electrical units. In 1881, the International Commission on the Definition of Electrical Units agreed on a resistance standard corresponding largely with the suggestion of the German industrialist Werner von Siemens. But no German laboratory was in position to undertake the costly precision work on the exact representation of the ohm. So this was accomplished in England. Notice how they put the name for this measure of resistance as ohm, which is the actual Sanskrit om, which is the sound of creation. Very, very interesting. We'll go back to that later. Although Germany was second only to the United States as an exporting country, it had to import precision measuring equipment from England and France. Not only the German precision tool and optical industries, but leaders of scientific institutes as well deplored the quality of the optical and mechanical instruments and demanded an institute for further scientific instrumentation. Siemens and the physicist Hermann von Helmholtz argued that in such an institute, applied as well as general scientific problems should be investigated. In a letter to the Prussian Ministry of Education, Siemens emphasized the national advantages of a place where scientists could be freed from teaching duties to concentrate on research. The Reich would gain important material as well as idealistic advantages from a scientific workplace, he wrote. In the competition between nations presently waged so actively, the country that first set foot on new paths and first develops them into established branches of industry has a decisive upper hand. Not only power but prestige were at stake. It is not scientific education, but scientific accomplishment that assigns a nation to the position of honor among civilized people. Siemens lent further weight to his demands by donating a plot of land in Berlin for the financial foundation of the Institute. In 1887, the Physikalisch-Technische Reichenanstalt was founded with two departments, one technical mechanical and the other physical scientific. Research and testing duties for industry and military dominated PTR's early years, but Helmholtz, its first president, was placed a high value on fundamental research as the basis for technical innovation, and almost the entire scientific staff was made up of his university students. The PTR scientists could solve their assigned problems within a wider scientific context than could their colleagues in industry, and the PTR became one of the most important centers for the investigation of the properties of matter. It was a forerunner of national research establishments where the costs of innovation were socialized while the profitability of private firms was enhanced. The PTR's physical scientific department consisted of three groups: thermal, electrical, and optical. In the first years, why thermal, electrical, and optical? Because they're all properties of matter, but they're also properties of crystals. Let's continue. In the first years, the main work of the thermal group was to improve thermometers. For example, it investigated thermal expansion of various types of glass, manufactured chiefly by Zeiss and Schott. It also carried out pyrometric investigations in order to get a grasp on temperatures up to the melting point of platinum, a task that originated in the steel industry. Meanwhile, the electrical group looked for ways to determine more precisely the values of the fundamental electrical units. It also carried out magnetic measurements of iron and steel on commission for the German Navy. The Navy, finding that its compasses deviated up to 50% from the correct values because of the iron used in its ships and torpedoes, asked the PTR to investigate which types of steel exhibited the least residual magnetism. Likewise, the optical group existed to serve practical needs. Its first investigation stemmed from an 1889 petition of the German Association for Gas and Water Experts calling for the development of a reliable measure of illumination. The search focused on the emission from platinum foil at constant temperature as a standard for comparison. This search opened a series of radiation investigations, leading to the famous examination of the spectral energy distribution of black-body radiation that became a route for quantum mechanics. Besides this photometric work, the group carried out polarimetric investigations, prompted in 1891 by the German Association for the Beet Sugar Industry. The rotation of polarization by solutions could be used to determine the concentration of sugar and other organic substances. This is again how they determine what something is made of through light and the interplay of light and crystals. Let's continue. To find a standard comparison, investigations were carried out on quartz, which furthered understanding of the optical properties of solids. The PTR's importance, namely, that is to say, the optical properties of crystals. Let's continue. The PTR's importance for Germany's economic and scientific hegemony was recognized abroad by the turn of the century. Similar establishments were founded in all the major industrial nations: the National Physical Laboratory in England in 1900, the National Bureau of Standards in the US, the Laboratoire d'Essai in France, and in 1917 the Japanese Physical Chemical Institute Riken. The Göttingen Association for the Support of Applied Physics and Mathematics is an example of a different form of collaboration between university science and industry at the end of the 19th century. The impetus came from Felix Klein, professor at mathematics at Göttingen University. He was an eminence grise for the organization of science in Germany around 1900 because of his connections with Friedrich Althoff, the overseer of the Prussian Ministry of Education, and with influential industrialists such as Henry Theodor Bottinger, a director of the Bayer dye factory and a representative in the Prussian Diet. Klein realized that German industrialists might be willing to support applied science financially if he spurred them with the threat of foreign competition. The chemical industry took the lead in 1896 when, with Boettinger's support, the Institute for Physical Chemistry and Electrochemistry was founded at Göttingen and put under the leadership of Walter Nernst. A year later, donations from industry enabled an applied physics department to be established at the university's Physics Institute. Meanwhile, in 1896, industry's support of science at the university was institutionalized in Göttinger Vereinigung. The founding assembly announced that its aim was extending instruction and research in the area of applied physics. The association at once raised money for an institute for applied electricity. Investigations at the new applied institutes typically bordered purely scientific and purely applied disciplines: electrochemistry, electrometallurgy, theory of solids along with hydrodynamics and aerodynamics, and the theory of technology and magnetism. In the Göttinger Vereinigung, the common interests of science, industry, and the state brought diverging disciplines together again. In some, industry donated money, the state created prestige and positions, and science contributed to practical ends. This was a pattern that in the 20th century would create many other organizations that pursued large-scale interdisciplinary solid-state research. Anyway, 1.2, conceptions of solids in classical physics. The mechanical crystal. Franz Ernst Neumann's move in the fall of 1826 from the capital of Berlin to the remote city of Königsberg, a trip by post-chaise lasting 8 days and 8 nights, was the midpoint of a journey for classical physics, a journey during which crystals came to be understood in terms of the laws of mechanics. The development had begun in France with the mathematization of specialized physical knowledge, an approach Neumann carried with him in his head. Neumann had accepted his appointment to a provincial university reluctantly. He was to take over the teaching of mineralogy, an area in which Neumann had already won distinction from a professor who had been teaching nearly all the scientific disciplines. After only a few semesters, Neumann began to intersperse his mineralogy lectures with physical insights. So this is where we overlap, okay? The minerals and the matter. Neumann had become interested in physics in Berlin, where he particularly admired French work in the field. To master Fourier's book on heat theory, he copied it by hand, absorbing its mathematical approach. Neumann's first experimental studies were accordingly in the theory of heat. He depended on works by Alexis Therese Petit and Pierre-Louis Dulong that had recently appeared at the École Polytechnique, works that culminated in the law named after the pair. The Dulong-Petit law states that for simple bodies, the product of the specific heat and atomic weight is a constant. The French tended to place experiment in the foreground, and Neumann kept it there. He created no new theory, but extended known laws through further experiments. For example, he extended the Dulong-Petit law to compound materials. The extended law became known as the Kopp-Neumann rule. This work was published 3 decades later by one of his students. Neumann's habit of scarcely publishing anything makes it difficult to evaluate his contributions with precision. Turning from thermal measurements, Neumann next applied himself to 2 topics then of much interest: optics and the theory of elasticity. Interest in the connection between the two had recently revived when the wave theory of light triumphed over Newton's theory of light as a stream of particles, both of which are incorrect, by the way. But let's continue. Through work by Thomas Young and John Fresnel, even the skeptics became convinced that light is a wave in a light ether that interpenetrates all bodies. The key was the idea that the wave is transverse. This explained not only diffraction but polarization phenomena, including the rotation of the plane of polarization by certain substances, a phenomenon discovered at the beginning of the century. Again, that's incorrect. Light is a property of crystals, and the crystals can polarize it because it's themselves that they're polarizing. But let's continue. Fresnel's ideas led to a momentous conclusion. Since transverse vibrations are possible only in solids, the ether had to be something like a solid. Thus, optics and mechanics were linked, and the theory of light would depend on a satisfactory mechanical theory of elasticity in solids. So it's not that light is a wave or ether exists. Ether doesn't exist. Ether comes from an incorrect translation of the word akasha in Sanskrit. But akasha means that is not. So what is not? Space, 3D space. So akasha means 3D space, which is a cavity. It's something that is not. It's a hole. It's a hole in matter. So anyway, let's. So they were talking about the theory of light, and what it depends on is in the mechanics and the elasticity of the solids and the vibrations of these solids, which are the crystals. But anyway, let's continue. There was already a long tradition of observations of elastic phenomena and attempts to describe them in a theory. However, despite much progress in solving individual problems, the sum of elasticity theory at the beginning of the 19th century has been described as an unsatisfactory theory of bending, an incorrect theory of torsion, an unproven theory of rod and plate vibrations, and the definition of Young's modulus. Along with the new hope, so that's the question: why do materials bend? Okay, that's what they were trying to answer. What is this property in the crystal that allows it to bend? Why are not all materials completely unbending? So that's the question. Along with the new hope of providing a theory for the light ether, elasticity had always held out hopes for practical applications, and this became more pressing as the 19th century opened. In the wake of Napoleon's military expeditions, analysis of the construction of roads, bridges, and even fortresses received enormous impetus through numerous prize competitions. For example, in 1808, the question of vibrating plates was offered, drawing the attention of scholars to problems of surface elasticity. Again, vibration and elasticity are linked. Louis Navier, a road and bridge engineer, responded with the equations of equilibrium and motion of a two-dimensional isotropic medium. He began with the Newtonian concept of molecules as material points connected by forces and supposed the forces to be proportional to the change in distance between the molecules, thereby deriving Hooke's law for the extension of a spring. But Navier's efforts to move up to three-dimensional equations failed. Today we know that one needs more than the single elasticity constant that he defined with reference to Young's spring modulus. The problem found a surprising solution. Auguste Cauchy, after resigning his professorship in road and bridge engineering at the École Polytechnique, concerned himself with the elasticity of solids. To describe the behavior of an isotropic body, he introduced a quantity that was a collection of 21 independent coefficients, a symmetric tension and deformation tensor in modern terminology. In 1827, Cauchy formulated general equations on the basis of a model of the solids as a continuum. This was the foundation of classical linear elasticity theory. However, when he extended these ideas to anisotropic substances, such as typical crystals, he was forced to abandon the continuum and imagine the substance as a lattice of material points linked by attractive and repulsive forces. Taking the known geometric systems under which such three-dimensional space lattices could be grouped, he found relationships among the various elasticity coefficients, reducing the number of coefficients from 21 to 15 in the general case and to 2 for the simplest lattice, the cubic system. Again, this is all crystals. However, experiments failed to demonstrate these Cauchy relations. The large number of coefficients became the subject of a decades-long debate among physicists. The community split into supporters of the multiple constants theory and the reduced constants theory, a question not settled, as we shall see, until the 20th century. When Neumann took up the entire complex of questions in 1832, he agreed with Navier's theory based on Newtonian point molecules. Neumann managed to rigorously derive a theory for the interaction of light and matter, making the mechanical theory of elasticity the basis for optics. One result was an understanding of birefringence, the splitting of an image by certain anisotropic crystals. This phenomenon depends on the differing velocities of propagation of light in different directions, as Fresnel had determined through observation. Neumann went further. For example, he described in mechanical terms the birefringence that appears when an isotropic body is subjected to pressure or uneven heating. Such matters had to be considered from a new angle later in the century as James Maxwell's electromagnetic theory of light gradually supplanted the simple mechanical theory. The new ideas gave new motives for work on crystals. For example, Heinrich Rubens, a professor at the Technical University in Berlin, Charlottenburg, was solidly convinced of the validity of Maxwell's theory. He did not use radiation to understand crystals, but he used crystals to understand the spectrum of electromagnetic radiation. So there, you see, there's a guy that knows. It's the crystals that emit the radiation. It's the electromagnetic radiation is a property of crystals and not the opposite. He pursued the invisible heat radiation that had already occupied numerous researchers, measuring how the refractive index of quartz depends on wavelength. Rubens found indications of absorption, in particular infrared wavelength ranges. By 1896, he had hunted down and described what he named the residual radiation bands. He saw these as a filter that would allow him to separate out an almost monochromatic beam from the broad band of infrared radiation that his sources produced. But as well as we should note later, the values that he and his students measured were not just useful for studying radiation. They gave a decisive impetus to work on the dynamics of crystal lattices. Neumann's contribution to this later work would come through his students. In 1876, he retired because of age. Following his wishes, his teaching studies were taken up by Waldemar Voigt, who had taken his degree on the elasticity of rock salt under Neumann. Voigt's research, devoted in the following years to elasticity theory and its application to optics, was in the spirit of Neumann's work. When in 1883 he accepted a call to Göttingen, Voigt brought the Königsberg traditions with him. While lecturing on mathematical physics, he devoted himself to experimental work. To Voigt, measurements of elastic and piezoelectric constants, of pyroelectricity, of magnetization, and of optical constants of transparent, absorbing, or optical active bodies all fell under crystal physics. Again, to Voigt, all these properties of matter, of physics, fell under crystal physics. There's a guy that knows. And you know what? I actually just ordered 2 books from this guy. They're in German, so I'll have to do videos on, with the translation there when I read them. And they're all talking about crystal physics. He devoted himself to experimental work. That area in which the music of physical laws sounds in full and rich chords as in no other area of physics. So they're quoting him on the crystal physics. And what does he have to say about crystal physics? He says, in which the music of physical laws sounds in full and rich chords as in no other area of physics. And this is a guy that knows. He's telling you the truth right here. He's telling you about the laws of sound. He's telling you about the physical laws of sound, how the universe is created, how matter is created by sound, in chords, musical chords, okay? So, and this is what, I mean, you can read this in the Bible, where God makes the world through the word, through the sound, and you can also read it in the Bhagavad Gita, especially in the new multi-dimensional decoding that I'm doing, and I'll come out with that as soon as possible, and I'll publish that and let you know. But this is the real deal right here. This is the guy that found the truth. He unraveled the veil, or more precisely, God allowed him to do so. Anyway, let's continue. At first, he held to the elastic theory of light, and when he moved in the direction of Maxwell's theory, he was criticized for having brought the entire Neumann school into disrepute. So he returned to a purely phenomenological way of thinking, seldom asking about the mechanics of a process. This style of work in crystal optics brought great success to him and his favorite students, Paul Drude and Friedrich Pockels. In 1910, he published his monumental book on crystal physics, dedicated to Neumann's memory. Here Voigt summed up his life's work, the great glorious area whose cultivation I have returned to again, and again for the last 36 years. And that's the book I ordered. So I'll share my findings there with you guys. It should be pretty astounding. Crystallographers before Voigt had connected physical properties with crystal structures in their books, yet he was the first to bring all the crystallographers' theories about structure together in a physics textbook. He could rightly claim to be pioneering the path to the promised land of crystal physics through the desert of crystallography. He described in detail the effects of heat, electricity, magnetism, and pressure using experimental results, including error analysis, and he tried to provide a theoretical explanation based strictly on classical mechanics, mechanical and thermodynamic laws. Not once did his textbook mention Maxwell's equations or even the emergent microscopic notions of matter. Despite what was already an old-fashioned standpoint, Voigt's book remained current as a basic source for a unified mechanical crystal theory because of its completeness. It was an inexhaustible mine for all physical questions on crystals. The Bible for workers in this field. And this guy is not including any of the BS. Okay, that's why it's so helpful. That's pretty amazing. This is it right here, guys. I've just proved to you what these guys know down in the deepest levels of academia. As one of the last supporters of a school with outdated views, Voigt would be overshadowed by the growing acceptance of Maxwell's theory, right? Because they have to push the hoax, right? By the revolutionary quantum physics, which is again all a hoax to hide the magic of the crystals, because they communicate telepathically. So how do they cover it up? With BS quantum mechanics. By the X-ray experiments that would make the crystal lattice visible. So again, X-ray experiments that would make the crystal lattice visible. What is that? Those are the electron microscopes that tell you they're looking at electrons. That's CGI. What they're really looking at is the smallest crystal lattices when they're forming from the unmanifest to the manifest through divine geometry, sacred geometry that God uses to build his universe. In his personal life, he would not recover from the defeat of Germany in the First World War with the loss of his international ties and friendships, but something of his way of thinking passed on from Neumann and the French before him survives. Voigt saw his research not only as mental work and the fulfillment of his desire for knowledge, but also as an aesthetic duty, a devotion and expression of his personality. He would certainly not have wanted to be called a father of solid-state physics, insofar as that became a practical-minded science. In fact, the central message of his textbook was a specific method of looking at things that could scarcely have been more abstract and ideal. This method seems so inevitable today that it is hard to imagine that physics ever lacked it. But it arose only late in the 19th century out of crystal studies, and it's perhaps the greatest contribution such studies have made to scientific thought, analysis through symmetry. I'm going to stop right there, guys. I'll continue another video. It's been a great time with you. God bless.